Okay, so we have a cylindrical can that's supposed to hold 1 liter or 1,000 cubic centimeters of oil. We want to find the dimensions that will minimize the surface area and therefore the cost to make the can. And in this video, we're going to set up the problem. We're going to find the optimization function and the domain of this. All right. So it says here we want to minimize surface area. Maybe I should draw a little picture of the can so we can get an idea what we're looking at here. And I suppose by dimensions, what we mean is the height of the can and that radius. And what we want to do is minimize the surface area. So if we have a function for surface area, we're going to find the minimum value when you take a derivative and set it equal to 0, right? That's where the minimum value is going to be. So the first thing we do is get this function. All right, so what does the surface area of a cylinder look like? All right, so I guess we have top, we have a bottom, and we have these sides. Well, the side's a whole circular thing coming all around here, but I guess that's what I mean by side, right? It's all that stuff all wrapped out. The top and the bottom, we can take a look, right? They're just circles. And the area of a circle with radius r is just pi r squared. And now for this side. So what you want to do is you want to imagine we cut this thing and then we unravel it to make a rectangle. If you take a piece of paper and you fold it up into a cylinder, you'll see what I'm talking about here. But just so you know, the rectangle that's the paper, then you fold it around to make the cylinder. All right, and if we look at this, area of rectangles, of course, base times height. I can see the height right here. That's just gonna be my h. Then the base of my circle is the base of my rectangle is the distance around the circle. All right, that's what I have here for that base. And the distance around a circle, we have a name for that, which is circumference. And so there we go. That's the other length right there, 2 pi r. So if we want to have a surface area function, I guess we're going to be adding 2 pi r times h right there. I guess that looks kind of messy, but base times height, right? So if we add all that up, pi r squared plus pi r squared is 2 pi r squared for the top and the bottom, plus 2 pi r times h for the sides. All right. But we have a problem here in that I have 2 variables. So we're going to have to eliminate one of those variables. And I guess that's where our constraint's going to come in. That we hold 1,000 cubic centimeters of oil cubic centimeters indicates that we're talking about a volume. And then I guess what's the volume of a can? Well, I guess that's just what area of the base times the height. So, all right, that was going to be our constraint. I know if I take pi r squared times the height, I'm going to get 1,000 cubic centimeters. So I suppose it makes sense then to look at the height right here. That h right there and that h right there. Theoretically, we could solve for the r, but that just looks harder. So that'll tell us that h is 1,000 divided by pi r squared. Then if I plug all this in, I get a function just in terms of r. Two pi r squared plus 2 pi r times 1,000 over pi r squared. Then I guess we can do some reducing right here. I'm going to end up with 2 pi r squared plus 2,000 over r. Now there we have our objective function. This is the thing, if I take its derivative and set it equal to 0, I can find the radius that will give us the minimum surface area. But there's one other thing we should talk about now that we have this function. We should mention its domain. And again, note that my variable is r, right? So it's in terms of r. Well, it's a radius of a can, so my r has to be positive, clearly. But what other restrictions? Do I have an upper bound on this? And if we look back here, our height of our can also has to be positive. So that means 1,000 over pi r squared has to be positive. And this is just always going to be true, right? No matter how big r gets, we're never going to get a negative value out of this. So this whole thing, this whole h, as long as r is positive, it'll never be negative. And then so there's no upper bound. So my domain is just r is positive. R, we like to put it in integral notation as 0 to infinity. Okay, there we go. So there is the objective function and its domain. And in the next video, I'll finish up the answer.